Good morning, everybody. Okay, so we're starting a new semester and a new chapter. We're going into my personal favorite part of physical science. We're going into the physics part. And we're starting chapter 2, which is about motion. And section 1 is describing motion. Now, the main idea of this particular session is two-part. The first part is that position, that is your location, position describes where an object is, and speed describes how fast the object is moving. So that's the main idea here. Position describes where an object is, and speed describes how fast it is moving. Okay? So let's get started. Now, the first thing we have to learn to do when we're describing motion is learn how to describe the location of an object. There are a number of ways to do it, and we're going to look at the simplest ways. When you describe the location of an object, you describe it by its position. We use an X to describe position. Think about it. X marks the spot on a treasure map, doesn't it? So X is the location, the position, and it's always relative to a reference point. You have to know from where you're looking. Let's look at an example of what I'm talking about. Here I have a grid of a town, and we're going to take the post office to be the center of the grid, 0, 0. And other things around town can be described, their location, their position can be described relative to the location of the post office. Okay? I'm going to call this bus 1, and this is bus 2. This is house 1, and this is house 2, and then we've got the mail truck and we've got a red car. Okay? So now what we're going to do first is describe the position of some of these objects on this grid using Cartesian positions. Now, Cartesian just means you've got an XY grid and you're going to use XY coordinates. You know, X, comma, Y, over, up, over, down, okay? So from the post office, let's find the position of bus 1. From the post office, we would go 2 in the negative direction, because here's 0, 0, positive, negative, okay? -2 and -3. So up here we'd say -2 in the Y, X direction, and -3 in the Y direction, okay? Now, let's look at house 1. House 1 is located from the post office, 0 in the positive or negative X direction. We don't have to go left or right. We're just going to go up 3, and that's in the positive Y direction, so that would be +3. So 0, +3. That's the position of house 1 from the post office. Now let's try the red car. From the post office, we're going to go 2 in the negative direction, in the negative X direction, and 2 in the positive Y direction. So we're going to say -2 and +2. -2X, +2Y. Okay? So we can use Cartesian coordinates to locate objects relative to a reference point. In this case, the reference point being the post office located at the origin. Now, we can use this same grid and do the same thing a slightly different way. We could use cardinal directions for our positions. Now, Cartesian means you're going to say X, comma, Y. Cardinal means you're going to use compass directions. Now, if you don't know it, I'm going to show you right now. Standard compass directions on a paper, north is up, south is down. East is to the right, west is to the left. In fact, we call this a compass rose, okay? So, in fact, look right here. North points up, all right? So south is down, east is to the right, and west is to the left. So let's find the coordinates or location or position of each of these same objects with reference to cardinal directions. So, bus 1, you're going to go 2 squares to the west and 3 squares south. So we're going to say 2 west and 3 south, because that's what we have to do to get there. So 2 west, 3 south. There it is. Okay? Now, let's take a look at house 1 right up here. Now, notice from the post office, do we need to go east or west? No, we don't. All we have to do is go north 1, 2, 3 spaces. So we're going to say 3 north. And that is the location relative to the post office of house 1 with cardinal directions. Okay? Now let's try the red car again. To get to the red car, we've got to go 2 to the west, and then we have to go 2 to the north. So that's the location of the red car relative to the post office. Okay? So the post office is our reference point, and then we've located the position of several of the objects relative to that reference point. We've used Cartesian positions, x, y, and we've used cardinal positions using north, south, east, and west. Okay? All right. Now, if an object moves, that means it's going to change location. It's going to change position. So let's look at what happens when an object changes position. When it changes position or location, okay, it is undergoing motion. Motion is a change in an object's position relative to a reference point, like the post office. Now, there are 2 ways that we can describe motion, and we're going to be learning about both of them in this chapter, okay? The first way is by using scalar quantities. Now, this is a term you may not have heard before. A scalar quantity is any quantity which is described or has magnitude only. Now, magnitude is simply a fancy word for how big something is, the numerical value that you use to describe its size. For example, an example of a scalar quantity is mass. So you might have a 10 kilogram mass. Well, 10 kilograms would be the magnitude. That's how big the mass is, 10 kilograms. Okay? But mass is a quantity that doesn't point, so it doesn't have a direction. If you've got a book sitting on a table, it's got mass, but that quantity mass doesn't point, so it's a scalar quantity. Some other examples, energy. You could have 10 joules of energy. That's the magnitude, 10 joules. Another example of a scalar is time. 50 seconds. That would be how big the measure of time is. And distance, which we'll look at in a minute. Distance is described only by how big the distance is. For example, 10 meters. That's how big it is. Now, some quantities are not scalars, they're vectors, and we can also use these to describe motion, but they're a little more involved because a vector is a quantity that has both magnitude and it has a direction. For example, force is a vector quantity. Now, as you know, a force is a push or a pull. But think about it. If you push with 10 newtons of force, can you push without pushing in a direction? No, of course you can't. Anytime you push on something, you're pushing in a particular direction. So direction is an inherent part of a force, and that makes the force a vector quantity. So, for example, the force might be 10 newtons east. So that's a vector quantity. It has magnitude and it has direction. Okay? Some other examples of vectors are velocity. And something we'll talk about today, displacement. And there's plenty of other examples, but we don't need to list them all here. Those are sufficient. Okay, now let's talk about these two quantities and how we can use them to describe motion. Remember, we're looking right now at describing change in location. Well, let's see. What is change in location as a scalar quantity? Well, that is distance. Distance is a change in position. We use a letter D to represent distance, and the SI unit of measure is the meter. But it's important to understand what distance is, since it only has magnitude or numerical size. It does not have a direction like a vector. So direction makes no difference to a distance. That means that distance is the scalar change in position, which is a path length between 2 points. Okay? So, for example, look down here at this runner on this field. Here is the zero or goal line. And then you've got 10 meters, 20 meters, 30 meters, 40 meters, 50 meters. The person starts at 0 meters. He travels down the field, turns around and comes back and ends up right here at 20 meters. So what is the distance traveled by the runner? Well, it's just the path length between the starting and end point. So we go 10, 20, 30, 40, 50, 60, 70, 80. 50 plus 30. All right, so 50 meters plus 30 meters is 80 meters total distance traveled by that person. That's the path length they followed, okay? But now the other way of describing change in position is using a vector. And this vector is called displacement. Now, to distinguish the D for displacement from the D for distance, we use this funny little sideways check mark over the D. That makes it a vector quantity as opposed to a scalar quantity. So now it has magnitude, but it also has direction. The SI unit is still the same though, because we're still measuring how far. It's just how we measure how far that makes a difference. Notice what this says. It's a vector change in position that is the straight line path between 2 points. A straight line path between 2 points from beginning to end. So notice, right here, we started here, we ended here. The straight line path from one to the other is this. He started, he went this way and ended up right there. Doesn't matter what the path length is. Doesn't matter that he turned around. We're only looking at the beginning and the end points. That's all. We don't care about the path in between. So this arrow represents the displacement. The object or the person started here on the goal line and ended here on the 20-meter line, so their displacement from beginning to end was 20 meters to the right. Okay, so look right here. We would say 20 meters, all right, to the right. You could also say, if you knew which directions were which, for cardinal directions, you could say 20 meters east, or you could say 20 meters in the positive x direction if you wished, okay? But for our purposes, to the right is fine because we're showing two directions here, to the right and to the left. So to the right is fine. So this person started here, they ended here, so their displacement is to the right and it's 20 meters long. So notice there is a difference between displacement and distance. Now, let's look at another example, and I'm just going to jot it in right here. You don't really have to do this, just watch. Suppose you start from home and you're going to go to school over here. Now, as you know, here in Bradenton, the roads are not laid out straight from one place to another place. You've got to do some weird stuff, okay? All right? So it might be something like that. You might have to jog up or down, or you might have to go a little further south and come back. The point is, this is the path you follow with your car because there's no road that goes straight from home to school. So you have to follow the road, and sometimes the road is not perfectly straight, is it? So the distance you travel is all of these little distances add up, okay? You just add this one and this one and this one and this one and this one, and you get the total path length or the distance you traveled to school. Your displacement, however, looks like this. Your displacement is the straight line path, even though you're not actually following it. Your displacement from where you started is the straight line path between those 2 points, regardless of what path you actually followed. So that's the difference between the distance and the displacement. Okay? One is the path length actually followed. The other is the straight line between the 2 points, pointing from beginning toward end. Okay? All right. Now, let's look at a little more. Notice, in this picture, we've got some more displacements. All right? And you can't see the arrowheads on these very well. I'm sorry about that, but there's a little arrowhead here and a little arrowhead there and one there. Let's suppose you went 5 meters east, stopped for a while, and then 5 meters east again. So your total displacement from start to end is the sum of those two. It's 10 meters to the east. But what if you went 10 meters east, realized you forgot something, turned around and went back 5 meters west? Then your displacement from where you started to where you're ended is this right here. It's 5 meters east. So notice, here we have the start, here we have the end point, and the resulting sum, the resulting vector, points from start to end. Right here, we went 10 meters east, so we started here. We went 5 meters west, so we ended there. The resulting displacement vector goes from start towards the end. Here it is right here, okay? We actually had to subtract. Here we added. 5 and 5 is 10. Here we subtract because they're opposite directions. 10, take away 5. You end up with 5 from where you started in the east direction. Sometimes they're not even in the same plane. Look at this one. Suppose you start right here, you travel 4 meters east, and then you turn left and travel 3 meters north. That means you actually end up, even though this is the path length, you actually end up this far from where you started to where you ended. So you end up a displacement of 5 meters north of east, okay? Now, kind of an interesting way to look at it, isn't it? But displacement is a vector, all right? Now, notice that in all of these cases, we are using arrows to represent the vector quantity. And that's always true. Anytime you have a vector, you can represent it on a diagram like this with an arrow. Now, why can you do that? Well, it's simple, okay? It's because arrows if you change the length, you're showing magnitude. Bigger the arrow, the bigger the numerical value. Okay, so the length represents magnitude. The bigger the arrow, or the longer the arrow, the bigger the number represented. All right, for example, 5, 10, 15. Okay, get the idea? All right, arrows also point. So wherever you point the arrow, it should be the direction of that particular vector. So arrows, because they can show magnitude and direction, are excellent ways of representing a vector quantity in a diagram, like displacements. Okay? Now, so we've looked at position, the location of an object. We've looked at distance and displacement. Both are changes in position. Now, let's take it one step further. Let's look at rate of change in location. Now, what does that mean? Okay, well, that means you have to first understand the word rate. What does that mean? Well, a rate is a ratio that specifically has time in the denominator. If you have a ratio and it has time in the denominator, I don't care what's in the numerator. It's a rate because it has time in the denominator. Some examples of rate that we're going to be looking at. Speed, which we'll look at today. Velocity is a rate. Power is a rate. It's the rate of work done. Electric current is also a rate. It's the rate of charge flow. Okay? So, how are we going to use rate to describe change in location? All right? Rate of change in location, rate of change in position. In this case, we're going to look at scalar today. We'll look at vector later. All right? If you're using scalar quantities, then we talk about the speed of the object. And we use an S for speed. All right? It's the rate of change in position or rate of distance because change in position is distance. Those are the same thing. So all we have to do to find speed is remember it's the rate, that means time in the denominator, of distance, distance in the numerator. So here we go. Here's a ratio symbol, and we're going to put time in the denominator. To make it speed, we put distance in the numerator. So since distance is a scalar, speed is also a scalar quantity. No direction involved, only path length. And the speed is how fast you traveled that path length. The distance per unit time, the meters per second. So those are the SI units for speed, meters per second. Now that doesn't mean there aren't other ways to measure speed. Of course there are. You see it in your car on your speedometer all the time. You see miles per hour and you see kilometers per hour. And it's okay to use those if they're in the problem, as long as you don't try to mix meters, kilometers, and miles with hours and seconds. You can't say meters per hour and you can't say miles per second. Okay? So it's either meters per second, kilometers per hour, or miles per hour. Don't try to mix them. Now, these are commonly used simply because we see them on our speedometer, but this is the SI unit of measure that we need to remember. Now, I'm going to show you a neat little trick, because when you are given a problem in science, and you're asked to find the speed, the rate of distance traveled, sometimes it's not the speed you're looking for. Sometimes it's the distance. Sometimes it's the time. For example, how long did it take? How far did the object go? So, how do you do the algebra? How do you manipulate the variables so that you get the right expression to plug your numbers into? Well, that's where this comes into play. You're going to like this. I really like this too. We're going to start by putting speed equals distance over time. Okay, SDT. All right, SDT. So just kind of slide that over, S dt. Now, this bar right here represents divide. And this one right here represents multiply. Okay? So now look, let me show you. If you're trying to find the speed, cover up the S, you're left with d divided by t. So that's how you find the speed. If you know the speed and you want the distance, cover up the distance. You're going to say speed times the time. Speed times the time. If you want to find the time, you're going to say the distance divided by the speed. Isn't that slick? That's how we do it, okay? Cover up the one you're looking for, and what's left tells you what to do. So speed, distance divided by time. If you want to find the distance, speed times the time. If you want to find the time, distance divided by the speed. How about that? That is pretty slick. Now, if you'll get a calculator so that you can see that you can do this on your calculator and make sure you can do it right, let's look at these examples. Suppose you have a car that's traveling at constant speed and it covers a distance of 750 meters, so there's the D, in 25 seconds. Seconds is a measure of time. So we know the distance and the time. We want to know what is the speed. So distance over time. We cover up the speed because we're looking for it, distance divided by time. So here we go. D over T. Always write your formula first. We have to show our work on all mathematical problems if you want full credit. All right, so distance, 750 meters. 25 seconds. Notice meters per second. We're going to end up with the right units. All right, so if you take your calculator and plug in 750 over 25, see what you get. Go ahead and pause right now, put that in your calculator, and see if you get that. Okay, now I hope you did, and if you did, that means you got 30 meters per second. Meters per second. So there's the speed of the car. Okay, that wasn't so bad, was it? No, it wasn't too bad. All right, next, number 2. A boat is traveling across a bay at a constant speed of 80 miles an hour. Oh, look, we're given the speed. And it says the bay is 15.8 miles wide. And we wanted the boat to cross the bay, so that's the distance it's going to move. We want to know how long does it take. What is that? Well, they're asking for the time. All right, so come up here, cover up the T. What do we have to do to get T? We have to say D over S. So we're going to say T equals D divided by S, just like on the triangle. All right, so now we take the distance. Oops, here it is, 15.8 miles. And we're going to divide by 80 miles per hour. Notice the miles will cancel. The hours, since it's in the denominator, it'll pop up to the top and we'll be left with hours of time. If you put that in your calculator, you're going to get this weird number. Go ahead and try it and see. Now, what should we do with that? Well, that looks kind of weird. So if you don't mind, I'm going to round it. Since 7 is bigger than 5, we can round and we can say 0.2 hours. And that's fine. Okay? All right. Last one now. Real quickly. How far will a tortoise travel, big tortoise, if he's moving at a constant speed of 0.5 meters per second? So there's our speed, S. For 1 minute, that's a time, T. Uh-oh, now we do have a problem, don't we? We have seconds here for the speed, but we've got our time in minutes. Now, is that going to help us? No, of course not. So what we need to do is convert 1 minute to seconds. Well, now, that's easy because we already know something about seconds and minutes. We know that there are 60 seconds in 1 minute. We all know that. That's daily common sense, isn't it? All right, so 1 minute equals 60 seconds. And that's what we're going to use for the time instead of 1 minute. That way it'll work with the seconds in this one, okay? Now, what are we trying to find? We're trying to find how far. We're trying to find the distance. So come back up here, cover up the D. To get the distance, we're going to say the speed times the time. All right, so let's write that out. We're going to say the distance equals the speed times the time. Okay? Now, that means we're going to say 0.05 meters per second times, not minutes, let's say seconds, 60 seconds. Now look, this will work. Seconds divided by seconds cancels. And we're left with meters of distance. 0.05 times 60, if you put that in your calculator, you should get 3 meters. So that old tortoise, in 1 minute, he's only going to travel 3 meters, okay? That's like about 9 feet, okay? Because look how slow he's going. Of course, you know, tortoise, they are slow. So there you go. Now, in a few days, we'll have a practice assignment on this, and you should be able to use your little triangle to help you solve these problems. Notice the process I went through, okay? I said, identify the information. Identify what I'm looking for. Then use the triangle to see what you need to do. And then plug in. Write your formula, plug in the values, get the answer. Not so bad, is it? Of course not. All right, well, thanks for listening. See you later. Bye-bye.